Good day. My name is Robert Cuter, and today I'm going to be doing a presentation for our water resource planning and management project for semester 1 2023 for a one-dimensional hydraulic flood modeling simulation using HEC RAS, where we have a scenario based on the Pongola River. The locality of this catchment is in South Africa's northeastern region, where it covers an approximate area of 15,000 square kilometers, and it's comprised of various ecosystems such as grasslands, savannas, and wetlands. The river originates in the highlands of Swaziland and flows for approximately 207 kilometers before entering the Indian Ocean. Here's a locality map where we can see the river with its catchment on the left-hand side, with all the various stations marked on there. The Indian Ocean's on the right-hand side, and the Mozambican borders on the top right. The objectives of this report will be to investigate various theoretical scenarios, carry out one-dimensional hydraulic flood modeling simulations using the HEC RAS software, and to report on the output data and findings. The given data which we received was a cross-section through the river reach number 1, table 1, which has got the variation of dimensions from river reach 1's cross-section, which will be applied later on. Table 2, which has got the return period versus the flood peak in cubic meters per second. For our scenario number 1, we would use a 2000 cubic meters per second flow and Manning's values of 0.020 and 0.015 for the channel, with a contraction and expansion coefficient of 0.1 and 0.3 respectively. Here we have the output table data from HEC RAS, where we can see from station 5000 to about station 3500, the velocity initially starts off at just below 5 meters per second, and then it suddenly ramps up to exceeding 5 meters per second, and then we reach around about station 2000, where it's further downstream, but we can see that the velocity just slows down and goes from 5 to 3 and below. What we can also see here is the Froude number. It's starting at supercritical, borderline on supercritical at about 1, and that's from station 5000 down to about station 2000, and then suddenly it goes well below 1, which means we're going back to subcritical. This is the 3D model of it, where we're just presenting a isometric view showing the actual channel arrangement and the water in the channel. With this profile, we can actually see the water level rising as the velocity is slowing down as it enters that area where the gradient flattens out. Over here we have our output data for the cross sections of the river. On the bottom right is the most upstream point, where we can see the water level is quite low, but it gradually tends to get deeper, especially from station 3500 back down to station 0. And there you can see in the top row of sections how the water level was increasing because of the gradient that flattened out in that area. Yeah, in our second scenario, we had two conditions. So the first one was for a 1 in 150 year flood peak of 12,600 cubic meters per second. And this was also using Manning's roughness coefficients of 0.025 and 0.015 for the channel. And contraction and expansion coefficients of 0.1 and 0.3 respectively. Over here we can see the output table where we're having very similar things happening to the previous one, where we've got the food number of 1 from station 5000 right the way down to station 2500, which means that this is supercritical, and then it enters an area there from 2000 down to 0 where it's subcritical. The exception here is because of the higher return period, our flow is increased. The velocities are also quite a bit higher. We're seeing velocities now in the region of 7 and 8 meters per second. Over here's the 3D isometric view again, where we can actually see the water level has now actually gone up on the side of the bank. There's a lot more water that's coming down the river at this stage. Now on the profile plot, we can actually see the depth of the water is substantially higher than what it was in the 2000 cubic meter per second example. And on the downstream from station 0 to about station 2500, we can see there's a dramatic increase in the depth of the water as the gradient is flatter there and it's backing up. So over here on our cross sections, we can see the water's quite a bit deeper throughout the entire flow of the river. Even at the bottom right, coming into the river, we're already quite a bit deeper because it's a higher return period, so our flow condition coming into the river is quite a bit higher. And as I've mentioned before, you can see on the first couple of sections here, which is from station 0 at the most downstream point, just how much higher the water is there. Then for our second scenario, in its second part, we had a 1 in 50 return period, which has got a peak flood flow of 10,000 cubic meters per second. And this was also using the same Manning's coefficients of 0.025 and 0.015 with contraction and expansion coefficients of 0.1 and 0.3 respectively, the same as scenario 1 and the first scenario of scenario 2. Okay, so on our results, what we can see again is the Froude number is still at supercritical flow from station 5000 down to station 2500, and then from 0 to station 2000 we are at a position of subcritical flow there. So it's the same results, it's just the magnitude that the results are playing out that's being affected. We're also still seeing velocities that are in the regions of 7 meters per second, which is similar to that of the 1 in 150 year condition. Here again is our 3D model with the isometric profile view, where we can see the downstream condition, water level just rising a bit. So here we can see again similar trend where the water level on the furthest downstream section actually gets deeper because of the flattened out gradient that we have. So this is the cross sections for the 10,000 cubic meters per second, 1 in 50 year recurrence. You can see that this is also flowing quite deep compared to our initial 2,000 cubic meter per second flow that we had, where we've got still coming in on the upstream quite deep, but at the downstream point we can see it's backed up because of that flatter gradient that we have there. Then for our final scenario number 3, we went back to a 2000 cubic meter per second flow, but it was considered with Manning's coefficients which have increased by 55 and 85% from the 0.025 and 0.015, and that gave us a new Manning's coefficient of 0.039 and 0.028 to be used in this scenario. Here's our output table, and again we see the same thing as with all the other scenarios, where from station 5000 till about station 3000 we've got a Froude number of 1, just on 1, which is indicating to us that it's supercritical, and from station 2500 down to 0 we've got a subcritical condition. Then what we're also seeing in this case, obviously with the flow that is 2000 with a higher Manning's coefficient, the velocities have come down quite a lot. So we, from station 5000 to about station 3000, it's come down to between 4 and 5, where it was at 7 on the other simulations that we had. And then it comes down even further from station 0 to 2500, where we add about 2 meters per second on our flow velocity. So over here on our 3D output, we can see the water level has subsided quite substantially with a slower flow. On our profile plot, we can also see that the water level has now dropped a bit, especially on the downstream side, even though it is still backed up quite a bit because we're entering that area where the velocity has been slowed down. And again, we've got on our cross-section data, we can see quite a low level on the furthest upstream on the far bottom right, and yeah, in the top row, top left, the water level has gone up a bit because of that flat condition that we've got. Okay, so now concluding remarks here for scenario number 1 for the 2000 cubic meters per second. We can see that the flow velocity increases, and we reach a point there at about station 2500 to station 3000 where suddenly the water flow velocity just drops off quite dramatically. We've also got that scenario where it's going from supercritical to subcritical. For scenario number 2, we can see that it's pretty much the same thing, where we've got a high velocity entering a lower velocity area, just the velocities are much higher because of the higher Q that we have here of 12,600 cubic meters per second for this 1 in 150 year occurrence interval. And obviously it's the same problem that we have with the supercritical flow entering a subcritical area. On our scenario number 2, with the second part, the 1 in 50 year return period, we see a 10,000 cubic meter per second flow, and that also we're seeing similar results here, where you've got this high velocity entering a low velocity area, and we've got the Froude number of 1 on the upstream higher velocity section, and then it enters a subcritical area as the Froude number goes below 1. Then for our final scenario number 3, for the adjusted Manning's coefficients, we're also seeing a similar scenario where from station 5000 down to station 3500, the flow velocities are around 5 meters per second, while station 3000 down to 0 is about 2 to 4 meters per second. Same thing's happening there, where we've got a supercritical flow from station 5000 down to station 3500, and then from station 3500 to station 0 we have a subcritical flow condition. And then finally, in closing, based on the simulations carried out above, it was observed that around station 3000 to station 2500 there's a rapid decrease in the velocity, while the grade from the river station 0 to station 2000 is relatively flat, and from 2000 to 5000 the grade increases. This basically causes a hydraulic jump, where the high velocity area just slows down and transforms into turbulent flow with a higher water depth. Based on the output data achieved by these simulations, it can be concluded that the higher flood occurrence interval with the yield of a higher peak is making it worse for these problems that we've identified above. When there's a rapid decrease in the velocity of the flow of the river, several changes can occur in the river's physical and ecological systems, with some effects of sediment deposition and water temperature changes, as well as oxygen levels that could be detrimental to animal and plant life.